Hello, my name is Christopher Mendoza. I'm currently a senior attending Capital High School in Santa Fe, New Mexico. I am working with my team made up of Zach and Joshua on an app named Solar Age. They will now introduce themselves.
My name is Zachariah Birch, and I am a sophomore at Capital High School.
My name is Joshua Tamara, and I'm a junior at Capital High School.
We were inspired by this theme of this challenge because firstly, we have 320 days of sun, which is our natural resource. Also, the impact of global warming that is increasing our annual global temperatures, as you can see on this chart created by NASA. And lastly, the world's use of fossil fuels and especially how we use oil at an unsustainable rate. And experts believe that we have reached the peak for oil extraction. We first designed an app using JavaScript language. In this app, the user has to type the daily electricity usage and cost. This is where PNM customers can get that on their utility bills. As we can see, there's 43 kilowatts an hour and $6. Our app calculates annual electricity usage and cost. It also displays the size of the PV system for this household, the total and the net price, which means the total price minus federal and state income tax credit, and it also shows the payoff time, or how many years it will take to pay off the system from what the homeowner saves on utility bills. We take this information from the PV Watts Calculator website created by the National Renewable Energy Lab. When we type in the zip code for that specific system, here we'll be using my schools, we'll be able to get the coordinates and also a map of where exactly that is. As we can see, we have direct current system size and we have 9. It's the same as on the app, and we get 15,960 kilowatts an hour per year. This is the same as in the app.
We then translated our JavaScript code to Python code, and we added a few more details, such as the type of PV system. The types of PV system are roof mounts, which are usually used for smaller houses, or for houses that most likely don't have a lot of yard space, and ground mounts or open racks for larger houses.
As you see on the graph, the maximum production of energy takes place in May, which first surprised us. But then we figured out that it may be caused by the fact that the monsoon season starts here in the middle of June, and then we have cloudy afternoons very often. Thanks to this graph, we then understood why it is necessary to type in the zip code there in PV Watts Calculator.
We also learned about solar trackers, which are the most efficient because they produce the most energy. We have also been working with David, a retired electrical engineer from Silicon Valley, on writing a computational mathematical model, and here they are. This shows how the efficiency of a PV panel changes when we tilt the panel towards the sun at different angles. In general, what we've learned from this model is that the perfect angle is 90 degrees. This is when the panel produces the most amount of electricity and when the shadow is the biggest. The further from 90 degrees, the smaller the shadow and less energy is produced. The red line here illustrates our ideal model, but David went further and created a prototype. This was a mini solar panel controlled by an Arduino that rotates at different angles towards the sun and outputs the amount of electricity produced by the panel. We added the lab results obtained by this prototype into this graph. As we can see, this green and blue line show that, and the green one is when we had clear skies, and the blue one is with wispy clouds. Our mathematical model seemed to be very close, but there's still a difference between our data and the model, since some of the sunlight bounces off the PV panel and is lost, so our panel does not produce the same amount of energy as our model. David already adjusted and improved the model using the curve fit function from the scientific library, and it is something that we are still working on together. Thank you so much for watching.